derivatives of trig functions. So at this point, hopefully, you've already done this first part, graph sine and f prime. So I'll do the same real quick. Boy, that goes to sleep fast. So clearing out these things from the homework. So we're going to do sine of x. We're going to make it bold. And then I'm going to graph the derivative of that. So that's math 8. Why are you not doing this? Oh, because I'm in the wrong place. I didn't move over quite far enough. So the derivative with respect to x of y2, I did them backwards, at x is equal to x. Since this is a trig function, I'm going to use zoom trig. So it's graphing the derivative right now. Man, that looks familiar. What is that? Yeah, it's the graph of cosine. And it turns out that indeed the derivative of sine is cosine. Now, you might think then that the derivative of cosine would be sine. Unfortunately, not quite true. So let's go back into this and change this function to cosine. So here's the derivative. You're like, that's not the sine graph, is it? It's the sine graph reflected over the y-axis. So it's the opposite of sine. So graphically, we think we know what's going on. We can prove it, but you have to know two limits. One of them you already know, that the limit as h goes to 0, sine of h over h is equal to 1. Another one that you may not know is this one. The limit as h goes to 0 of cosine of h minus 1 over h. That one, even though it's also 0 over 0, actually goes to 0. So here's how the proof goes. The derivative of sine would be the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Hopefully you're very used to that. By the way, on the AP exam, what they will do sometimes is they'll never ask you to find the derivative of something using the definition. But what they'll do sometimes is they'll throw a multiple choice question on there, and they'll give you something like this, except they'll give you it at pi over 3 or something, and you have to recognize that that's the derivative of sine at pi over 3. And then the derivative of sine, we're going to learn here, is cosine, which is what we thought, and then you just evaluate it at pi over 3. But you have to instantly recognize this, otherwise you're just kind of going, I'm not sure what to do with that. So we have to use the sum rule. The sum sine of x plus h is equal to sine x cosine h plus cosine x sine h minus the sine of x. And then what we're going to do is factor a sine out of the first and the last terms of that and split it from this middle term. So that what we end up with is the limit as h goes to 0 of sine of x times cosine h minus 1 over h, plus the limit as h goes to 0 of cosine of x of sine of h over h. And we recognize that one as being 1, and I just told you a moment ago that this limit goes to 0, so we end up with just cosine. I wanted you to at least see the proof. I'm not going to ask you to do any proofs like that. Partly because I'm like, okay, yeah, it involved knowing some tricky things. I don't care so much about the tricky things. So in a similar fashion, we can show that the derivative of cosine is negative sine. And now you can see an actual need for the product rule, for example. Before, when we were only doing polynomials, the usage of the product rule was kind of dumb. You should actually multiply them together first instead of doing the product rule. But here, we'll use the product rule to find that f prime of x is the first factor, x squared, times the derivative of the second factor, the derivative of sine of x being cosine x, plus the second factor, sine of x, times the derivative of the first factor, which is 2x. So that's x squared cosine x plus 2x sine x. We usually write polynomials in front of the trig functions because you could mistake the sine of x plus 2x for the sine of parentheses x times 2x, which would be the sine of 2x squared, which would be something else entirely. We can also use the quotient rule for ideas like this one. I've got u as cosine of t over 1 minus sine t, so du dt, the derivative of u with respect to the variable t, is going to be the denominator, 1 minus sine of t, times the derivative of the numerator, the derivative of cosine of t is negative sine of t, minus the numerator, cosine t, times the derivative of the denominator. Well, the derivative of the 1 is 0 minus the derivative of sine is cosine, so that's minus cosine t. All over the quantity 1 minus sine of t squared. That's going to be negative sine of t plus sine squared of t plus cosine squared of t over 1 minus sine of t quantity squared. Now, if this were a part of a free response question, you don't have to simplify it. But on the AP exam, it's unlikely that they're going to ask you something like this on something that's not multiple choice. So we need to simplify this. And this does simplify a fair bit because you notice sine squared t plus cosine squared t is what? 1. So we've got 1 minus sine of t over 1 minus sine of t quantity squared. So dividing out, I can just have 1 over 1 minus sine of t. All right, let's move on. So weight is hanging from a spring and is stretched from its at-rest position at time at y equals 0, 6 units. So stretched downward to y equals -6, then released at time t is equal to 0 so that its position is -6 cosine t on the time interval from 0 to 15. What are the velocity and acceleration at time t, and then describe the motion? So we have the position function, so the velocity function will be the derivative of that. So it'll be -6 times the derivative of cosine, which is negative sine t, which is equal to 6 sine of t. And the acceleration is going to be the derivative of the 6 sine t, so that'll be 6 cosine t. All right, so we know that when we release the spring, it's going to be moving upward, but the question is, how long does it move upwards? Well, I'm going to need to find when is the velocity equal to 0. So when is 6 sine of t equal to 0? Well, the 6 has nothing to do with it. Sine of t is equal to 0 when t is equal to 0, and then pi, 2 pi. And the question becomes, well, how far do we have to go on this? Well, we're supposed to go to 15, so that's going to be a little less than 5 pi. So 3 pi and 4 pi. So the weight starts at position y equals -6 at time t is equal to 0. The weight then moves upwards until t is equal to pi at position. So going back to the position, cosine at pi is -1, so y would be equal to 6. So then the weight moves downward until t is equal to 2 pi at position y is going to be -6 at that point. And then it just keeps oscillating back and forth. This is your classic oscillating motion that doesn't get dampened, which is what actually happens over time. And depending on what kind of a spring it is, but over time it's pretty quick that it's the oscillation starts decreasing. All right. In the interest of time, we won't do any more of that. Derivatives of other trig functions. For the other trig functions, you can use the quotient rule to find their derivatives if you know the derivatives of sine and cosine. So if we're trying to find the derivative with respect to x of tangent of x, that's the same as the derivative with respect to x of sine of x over cosine of x. So using the quotient rule, we'll have the denominator, cosine of x, times the derivative of the denominator, also cosine of x, minus the numerator, sine of x, times the derivative of the denominator, which is negative sine of x. Over cosine of x quantity squared. In the numerator, we're going to have cosine squared of x plus sine squared x. And then that'll all be over cosine squared x. So that's 1 over cosine squared x. And since 1 over cosine is secant, this is secant squared of x. So the derivative with respect to x of tangent of x is secant squared of x. In a like manner, we can find the other trig derivatives. The derivative of cotangent of x is negative cosecant squared. The derivative of secant, we can find that that turns out to be secant times tangent. And the derivative of cosecant of x is negative cosecant of x cotangent of x. One of the things to notice is that the derivative of all the cofunctions are negative, or the opposite of. The other thing that helped me keep track of it when I was first learning this, back while the Earth was still cooling, is that with the tangents and the cotangents and all of that, there's always 2 of the secants and 1 of the tangents in every one of them. See, this has 2 secants and 1 tangent. This has 2 secants and 1 tangent. That helped me keep track of which one was which. If that helps you, great. If you're one of those people who's just good at memorizing, you're like, I don't need silly things like that, Mr. Davis. That's fine also. All right, so let's find the equations for the lines that are tangent and normal to the graph of f of x equals tangent of x over x at x equals 2. You can use your calculator, support graphically. Okay, well, since it says you can use your calculator, I could use the quotient rule to find this derivative and then substitute in 2. But remember that your calculator will estimate the derivative at any point you like pretty quickly. So let me wake this back up and quit out of this and do math 8. To get to the derivative, I want the derivative with respect to x of tangent of x over x at x equals 2. So that's our slope. So f prime at 2 is our slope, is 3.433. And I guess I should say that's the slope of the tangent. And then f of 2 is going to be tangent of 2 over 2. So tangent of 2 bless you, copycat, is negative 1.093, we'll call it. So the tangent line will be y is equal to negative 1.093 plus 3.433 times x minus 2. And the normal line will be y is equal to negative 1.093 minus 1 over 3.433 times x minus 2. We'll come back and graph this if we have time. I want to make sure we get to the last part. So, and I think mostly just because it's fun, jerk is the derivative of acceleration. That may be, is that a new term to you? Have you ever talked about that in physics? Okay. Yeah, when you have a sudden change in acceleration, you feel that as jerk. So it's the third derivative of the position function. So if the position equation for a particle moving along the x-axis at time t between negative pi over 2 to pi over 2 is secant of t, find the equation for jerk. So the velocity will be the derivative of secant, which is secant of t times tangent of t. The acceleration will be the derivative of secant tangent. So we'll take the first factor, secant of t, times the derivative of tangent, which is secant squared of t, plus tangent of t times the derivative of secant of t, which is secant t tangent t. So this is secant cubed of t plus tangent squared of t times secant of t. And now it gets really ugly because they want us to take the derivative of that again. So the jerk, we don't have a rule. We can't use the power rule here because what I'm cubing is not the variable. I'm cubing the secant of t. So I have to think of that as being, for now, you'll learn a rule for this later, secant t times secant t times secant t. Basically, it's a three-part product rule. So here's how that works. What we're going to do is we're going to take the first two, so secant t times secant t, times the derivative of the third. So that'll be secant t tangent t. Plus, well, now we'll do the first and the third and take the derivative of the second, but that's just going to be the same thing, isn't it? And then we'll take the second and the third times the derivative of the first. They'll all be the same, and there'll be three of them. Then we'll do the same thing with the that'll be tangent t times tangent t times secant of t. That one's not quite as easy because they're not all the same. So keep the first two. I'll go ahead and call that tangent squared times the derivative of secant, which is secant t tangent t, plus, I'm going to keep the first and the third, that's tangent t secant t, times the derivative of tangent, which is secant squared, and then I'll keep the second and the third and take the derivative of the first. That's going to be the same as this one, so there'll be two of those. So that's 3 secant squared t tangent t plus tangent cubed t secant t plus 2 secant cubed t tangent t. What you notice is the first term, so it ends up being 5. Oh, actually, no, it's not, because that's secant squared. That's the end. Just a real quick thing to point out, when we took the derivative of that, we ended up with this. Notice if we do the power rule, we just get 3 secant squared t. Notice that it's multiplied times something else. Oh, this is secant cubed. Well, those first and last terms do add together. All right, that's it for today.